So last time, we talked about the idea of a double integral over a rectangle. And the idea was, say you had some kind of a surface, say this sort of a sheet right here, and you isolate some rectangle in the domain. You'd go through, and you would take each of these corners up to where they met their respective points on the surface, use the surface to describe the top end of this shape, and then you would focus your attention on the region underneath the surface but above the x-axis. And so we built a double integral to compute the volume of this. And so the double integral was nothing more than the volume of this solid formed above the rectangle in the domain but below the surface of the function above. Now there's one thing you might notice about this, is that there's absolutely no need for the region in the xy plane to be a rectangle. For example, if we had some other shape down here in the plane, maybe some irregular shape, it would still make sense to take each one of these points up and find their corresponding point on the surface, and then consider the solid region formed by taking that region in the xy plane, the top edge formed by the surface, and the vertical edges who form the sides. This would still give us a three-dimensional object, and so we could still talk about the volume of this object. And it makes sense to call the volume of this thing the double integral over the region, where the region is now sort of a more general shape than a rectangle, of whatever the function was who described the top end, this curve right at the top, z equals f of xy, with respect to a. So the notion of there being a volume makes complete sense. What about the idea of our actual formula? Remember that a double integral was defined by taking a summation of heights times delta x's times delta y's, where the sum was over a number of subrectangles. And then we took the limit as the number of those rectangles tended to infinity. Could we do something like that on a surface like this? If you think about it, we might run into an immediate problem. When we had a domain that was a rectangle in the xy plane, something like this, then when we subdivided this shape, we got smaller rectangles, and we knew how to compute the area of a rectangle like that. But if I had an object like the one we're looking at right here, some unusual or different looking shape, how should I subdivide this shape? I mean, do I slice it into smaller looking shapes like this? How would I subdivide it into smaller looking shapes like that? And even if I could, how would I work out the area of those little guys? Where would I stick a delta x and a delta y in this one? Well, it turns out we're going to do something pretty similar to this guy. What we'll do is we'll instead draw a big giant rectangle around this object, and then we'll subdivide that big rectangle instead. So in our three-dimensional picture, I'm going to take this shape, this region R, and subdivide it. And then what I'll do is I'll do exactly what we did last time. For each one of these rectangles, I'll find a sample point. Say this particular sample point right here. Given that sample point, which corresponds to this point in the three-dimensional picture, I'll go and find the height of that particular point on the function. I'll replace that part of the curved graph by a flat horizontal rectangular piece, and then convert this into a giant rectangle. And then I could compute the volume of this shape right here, and I could repeat that for every single point. If I find a specific point, say this point right here, that corresponds to this point in this picture right here, I know it's a little bit skewed, I'll find his corresponding y value up on the graph, replace that sliver of a graph with a flat horizontal piece of plane, and then work out the volume of this rectangle. What if I pick a point in one of the rectangles that lives inside the region, even though the whole region isn't there? Well, even if the region isn't completely contained in that rectangle, I could still approximate the volume above it by doing the same procedure. I mean, it's not going to be a perfect approximation, but remember, we're trying to approximate it. Finally, what if we pick a sample point that doesn't happen to be in any one of the regions at all? Say this particular part right here. Well, since that's not in the region in question, it should contribute no volume. And so I'll simply ignore this region entirely. I won't add it up. And so what I can do is go through and pick a sample point in each one of the remaining rectangles. Whenever a sample point is not in the region, I'll simply ignore those particular rectangles as not contributing any area, or any volume, sorry, on this particular approximation. Any of the regions which do have a point inside, then we'll go and we'll add up these volumes. The upshot is that we'll get a bunch of stacked rectangles, like skyscrapers packed together, who do a decent job of approximating the volume of that object. And so we can still make sense of the Riemann sum idea. It's a little bit more complicated, but the basic idea still holds. And then, as we use a finer and finer set of subdivisions, as the number of these rectangles gets larger and larger and larger, then we would expect, the approximation to get better. For example, here's a really nice computer-generated image of a Riemann sum that involves a large number of rectangles. And although I really can't tell you what the surface is, I've got a very good description, or at least a very good intuitive idea, of it being the surface where this is the graph of the function, and it's being taken over this sort of leaf-shaped domain right here. With enough rectangles, I can get a pretty good context of what's going on. And as the number of those rectangular prisms tends to infinity, we would get the exact volume. And so that's what we're going to define a double integral over a particular region as. So let's suppose that R is a nice region in the plane. Then we'll define the double integral of f of xy dA over the region R to be the limit of a specific kind of Riemann sum. Each one of these sums is supposed to represent a height of a rectangular prism, a length, and a width. And we're going to add up as many boxes as the sampling point xi, yi stays inside the region R. And then we're going to take a limit as the number of subrectangles tends to infinity. And we're going to call this a double integral over region R. Now, an obvious question is, what do I mean by nice? Well, it turns out that I can make the word nice a fairly precise word in a Calc 3 setting. What we mean is the following. First, R is bounded. It needs to be sort of finite in expanse. And two, the boundary of R consists of piecewise smooth curves. What does this mean? It means that whatever your region happens to look like, except at a couple of points, the in-between parts of the boundaries should be smooth in the sense that they have a well-defined tangent line at every single point. So that the only places where we don't have well-defined tangent lines along the boundary edge is at a couple of corners. The idea of these corners is that between two corners it seems like there's a nice piece of a boundary. In this case we would have 1, 2, 3, 4, 5 pieces of boundary. That's the idea of being piecewise smooth. So this shape right here, together with all of the points inside of it, would form a nice region, an integration region. Notice that the very, very first region we considered, namely a rectangle, very naturally fits this description. It's bounded, right? It doesn't run off to infinity in any direction. And with the exception of its 4 corners, it's completely flat, so it has nice tangent lines. In fact, it just has nice lines as its boundary edge right here. Now, before we look at a couple of examples, I'd like to at least summarize a couple of important properties that come out of this definition of a double integral. Now, our basic geometric interpretation has been that this is the volume of the solid region between R in the plane and the surface z equals f of xy. But that makes sense only if the surface is above the xy plane. If the surface was below the xy plane, then the double integral would be negative, since all of the z values are negative, in which case this double integral would represent the negative of this. So this is just like we had for an integral. This represents the signed difference of volumes formed by the solid between the region R and the plane. In other words, we take the volume of the part of this region above the xy plane, and we subtract the part of the volume of the region who lives below the xy plane. A second useful fact is that the basic rules of definite integrals still carry over. For example, if we have a constant times a function, then the constant can be pulled out of the double integral. Similarly, if we had a sum of two functions, an f of xy plus a g of xy dA, then the integral could be broken up for each one of the functions. We could find the double integral of the function f, and then the double integral of the function g, and simply add the two results together. So the scaling rule and the sum rule for derivatives make sense. The fourth rule, or the fourth basic property, might be said something like this. Suppose you have a function f of xy dA, and you wish to integrate it over some big region R. But you take that region and you chop it up into two smaller parts, R1 and R2. So you're looking at the signed volume of this function over the regions R1 and R2. Well, intuitively speaking, and we can verify this, we've taken one big volume and we've broken it up into two smaller pieces. We've taken the volume over the chunk that was region 1, we've taken the volume over the chunk that was region 2, and we simply add those up. So this allows me to break a region into smaller pieces. This is the analog of the Calc 1 notion that to integrate from A to B, you could integrate from A to C and then integrate from C to B. This is just that idea in two dimensions. Approximate the double integral of the function x plus 2y plus t dA over the region t if t is this triangular region shown below. So since we want to go and approximate what this integral is, and the only tool we've seen in our toolkit right now is the definition, let's go and do that. Let's just come up with a Riemann sum who approximates this. So the first thing we need to do is we need to come up with a rectangle that encloses this entire region. Maybe the most obvious candidate would just be this square right here. Next, let's subdivide this square into a number of pieces. I'll subdivide it into 9 equal portions. And then in each portion, I will pick, say, the midpoint. Now notice that by making this particular choice, 3 of these squares are not going to go and make any contributions to my Riemann sum at all. But for the remaining 6 squares, we can go through the process of the Riemann sum. So for example, for this first square, the sample point right here is going to be the point 1/6, 1/6. Remember, we chopped it into thirds, so this is the point 1/3 and 2/3, and so we're going to have 1/6, 2/6, 3/6, 4/6, and 5/6, kind of like the example we had in the previous podcast. So in this first square right here, the input value will be 1/6, 1/6. We'll plug that into the function to see the corresponding height. We're going to get 1/6 plus 2 times 1/6 plus 1, which is 6/6, which will give me a grand total of 9/6. That's the height of the first rectangle. To get the dimensions of the base, well, each one of these rectangles is exactly 1/30 unit long and 1/30 unit wide, so the base will be 1/3 by 1/3. And so this will give me a grand total of 9/54 units of volume right here. Next, I could focus on the second piece. The input value here is going to be the point 3/6, 1/6. So we'll plug that into the function to find its height. The height will be 3/6 plus 2 times y plus 1, which is 6/6, which will give me 11/6. Then, that's the height of this particular rectangular prism. The base, or the length and the width, are both 1/3, and so that'll give us a grand total of 11/54. If I were to go to this point right here, now granted, the whole region isn't inside of this particular rectangle, but the sample point was, and so we're still going to use this whole square to approximate area. So this was the point 5/6, 1/6. We plug that into the function because it is in the region we're integrating. We're going to get 5/6 plus 2y, 2/6 plus 1, 6/6, and that will get me 13/6 as the height above this particular point, times the length times the width, or 13/54. If we repeat this for the remaining 3 subdivisions, then we'll find that we have the following volumes of the 6 rectangular prisms. And so if we add up these total volumes, we're going to come up with a grand total of 78/54. or 13/9, which is approximately 1.44. So there's approximately 1.4 cubic units of volume underneath this particular plane, but above this rectangle right here. I might intuitively expect that this is an overestimate of the volume, since we're sort of adding portions of the base, volumes over these particular chunks right here, that weren't actually part of the region in question. So I might guess that the real volume is slightly less than that. In the last lecture, we saw a thing called Fubini's theorem, which allowed us to work out double integrals by doing iterated integrals. It turns out that Fubini's theorem does generalize, but we have to be a little bit more careful about it. So let's talk about what's sometimes known as a vertically simple region. So it's a region that has a well-defined top curve, say the top curve y equals t of x for top, and a well-defined bottom curve, y equals b of x. And then two well-defined vertical endpoints, the point x equals a, and the side x equals b. So a region like this is sometimes called vertically simple because it consists of nothing more than a collection of vertical lines who all have the same top curve and who all have the same bottom curve right here. Now imagine we had a vertically simple region that we'll call R. And let's suppose we want to work out a double integral over this region R. So I'll have some surface up here. Say this surface right like this. Z equals f of xy. And down here in the plane, I'm going to have my vertically simple surface, or vertically simple region. So the double integral would talk about this particular region right here, who has the surface as the top edge, the region as the bottom flat edge, and then vertical faces on the sides. Now, how might we find the volume of something like this? Well, imagine doing what we did when we proved Fubini's theorem in the last case. Well, let's imagine taking this thing and slicing it as if it was a loaf of bread. We'll get a bunch of very, very, very thin slices right here. And let's say that each one of these slices has a width of delta x. So a small, skinny slice right here. Well then, the double integral of this function over the region R would equal its volume. The volume would be approximated by adding up the volumes of each one of these thinly sliced wafers. Now this little tiny piece has a width of delta x. If we could work out the area of its face, then the volume of this thing would be approximately the area of the face times delta x. Now notice that different slices are going to have different areas. The area of this slice and the area of this particular slice are going to be different because this one is taller. So the area of this slice is actually going to depend on what particular x value you're at. In this particular picture, if x is close to the left-hand side, we're going to get a large area. If x is sort of in the middle right here, we're going to get a small area. So how would we work out exactly what this area is? Well, imagine standing right here and looking at it from the front. We would see this picture. We'd see the z-axis floating up. We would see the y-axis descending off to the right. And then we would see a vertical side, the surface up top, and another vertical side. Now, the curve up top is exactly this curve right here, f of xy, except that we're looking right now maybe at a fixed x value. So the area of this face is going to be nothing more than the integral of this function, f of x naught y, dy, evaluated from the left-hand side to the right-hand side. Now, what is this left value right here? Well, this leftmost value in the standing in front picture would actually be the bottom value in the three-dimensional picture, or this particular point on the bottom. Y would be b of x. On the other hand, the rightmost point, which would say be this point in the three-dimensional picture, would be the corresponding point on the top of this picture. The y value would be t of x. And so this would be the integral from b of x naught to t of x naught, if I'm at a particular x naught value. So we've just shown that this volume is approximated by adding up the area of a face, which was the integral from b of x naught to t of x naught, f of x naught comma y dy. We take that's the area of the face, we'll multiply that by delta x, which is the width. And now this represents the volume of a single wafer. Then we'll add up these wafers over all of the delta x slices, and we'll have an approximation. Of course, it's only approximation. If we wanted to make the volume exact, we would have to take a limit, as the number of those delta x slices went to infinity. But now focus your attention on this. We're taking the limit of a sum of function values times skinny wafers dx. That's exactly what an integral is supposed to do, is a limit of sums. This is going to be the same thing as simply integrating this expression with respect to x, where x goes from a, the left-hand side of the region, to b, the right-hand side of the region. This is sometimes called Fubini's general theorem. So let's summarize the statement one more time. Suppose that R is a nice, vertically simple region that takes the form R is equal to the set of all x values who stay between the left side x equals a and the right side x equals b, and whose y values stay above the curve c of x, but below the curve d of x. If f is continuous on this region, then the double integral over the region is equal to an iterated integral, where we first integrate with respect to y from the bottom curve to the top curve, and then we integrate with respect to x from the left side to the right side. Compute the double integral of x plus 2y plus 1 over the region T, if T is shown below. So remember, we already did this problem as an approximation, and we showed that the double integral was approximately 1.44, and that we guesstimated that this was an overestimate. So now let's see if we can work out an exact value using Fubini's theorem. So to apply Fubini's theorem, we have to first check that this is a vertically simple region. The easiest way to check that something is vertically simple is to draw a bunch of vertical lines, and to ask yourself whether or not every single one of these vertical lines has the same top curve and the same bottom curve. If the answer is yes, then this is vertically simple. In this case, every single one of these vertical lines that I've drawn have the same top curve, this diagonal line, and the same bottom curve, this horizontal line. And so this is a horizontally simple region. That means we can describe it as x going between two numbers and y going between two functions of x. So let's see if we can figure out what these are. This top curve right here, this is a line of slope -1 and a y-intercept of 1. So this is y equals -1, or negative x plus 1. The bottom is the horizontal line that forms the x-axis. And so that would be the equation y equals 0. And so the bottom curve is y equals 0, and the top curve is 1 minus x. What about the extreme x values? Well, the leftmost x value of this shape, the leftmost side of the triangle, is x equals 0. The rightmost x value, it'd be the point 1, 0, which means that x equals 1 is the rightmost value. And so here we've got this shape described as a horizontally simple region. So now let's use Fubini's theorem. Since we've described this region R as a vertically simple region, we can now use Fubini's theorem to compute the double integral exactly. It says take the function x plus 2y plus 1. We'll integrate it first with respect to y from the limits 0 to 1 minus x, bottom to top. Then we'll integrate that with respect to x from the left side to the right side. So let's focus on the inside bit first. According to the fundamental theorem of calculus, the inside bit will be the antiderivative of x plus 2y plus 1 dy, evaluated from y equals 0 to y equals 1 minus x. If we get an antiderivative, it would be xy plus y squared plus y, evaluated from y equals 0 to y equals 1 minus x. So if we plug those in, we're going to have x times 1 minus x plus y, or 1 minus x squared, plus y, 1 minus x. If we plug in 0, we're just going to get 0, so we'll subtract the results. This isn't going to contribute. If we clean up what we've got left, we're going to have x minus x squared plus, foiling this out, 1 minus 2x plus x squared plus 1 minus x. Now notice that the x here and the minus x here cancel, and the negative x squared here and the positive x squared here cancels, and so this simply simplifies to 2 minus 2x. And so that's the inner piece. We need to go and integrate from 0 to 1 the function 2 minus 2x dx. According to the fundamental theorem of calculus, we'll first come up with an antiderivative with respect to x, and then evaluate that from x equals 0 to x equals 1. The antiderivative, an antiderivative would be 2x minus x squared, which we can then plug in 0 and 1. Evaluated at 1, we're going to get 2 minus 1. Evaluated at 0, we're going to get 0 minus 0. And so if we clean these up, we have 2 minus 1, which is 1. And so there's our double integral. Notice that that's fairly consistent with what we had before. 1.4 is close to it, and 1.4 is certainly an overestimate. Compute the double integral of the function 6x squared y over r if r is the region shown below. Now, right now, the only tool we have in our arsenal is Fubini's theorem, which applies to vertically simple domains. However, if we go and draw a number of vertical lines to test this, notice that while all of our vertical lines have the exact same bottom edge, specifically the curve given by 4y equals x squared, they have different top edges. Some of these vertical lines have this diagonal line right here, y equals x, as their top edge, but others of these vertical lines have the horizontal line y equals 1 as their top edge. So it's not a vertically simple domain, and that means Fubini's theorem doesn't apply. Well, what could we do? Well, maybe the most obvious thing is that if we were to go right here at the point, or at the line x equals 1, and simply slice the region in half right here, we'd subdivide it into two regions, a region R1 and a region R2, and these two subregions would now be vertically simple. One of our basic properties of double integrals says that if we do that, the double integral over the region R will be the double integral over the region R1 plus the double integral over the region R2. And so this really boils down to computing two smaller double integrals using Fubini's theorem. So let's take that particular approach. So let's take the R1 integral first and see if we can describe the region R1 as a vertically simple domain. So to describe something as being vertically simple, we have to first find the upper and lower curves that define the y values. Well, the upper curve here is y equals x. The lower curve is given by this equation right here, 4y equals x squared. If we solve this for y, so we can write it as a function, y equals f of x, then we're going to get y is equal to 1/4 x squared. And so that becomes the bottom curve. What about the extreme x values? Well, the leftmost x value happens at the origin, that's x equals 0, and the rightmost x value is the point x equals 1, which is where we decided to split the regions up. So now that we have a vertically simple region, Fubini's theorem says that the double integral over the region R1 is going to be an iterated integral. We'll take 6x squared y, integrate it with respect to y from the bottom curve to the top curve, and then we'll take that and integrate it with respect to x from the left side to the right side. So let's focus on the inside bit first. If we use the fundamental theorem on the inside, the antiderivative of this with respect to y will be 3x squared y squared, which we can evaluate from y equals 1/4 x squared to y equals x, the bottom curve and the top curve. So when we plug in y equals x, we're going to get 3x squared times y, or x squared. When we plug in 1/4 x squared, we're going to get 3x squared times 1/4 x squared, quantity squared, and then we'll subtract these. So that'll get us a total of 3x to the 4th minus 3 times 1/16, or 3/16. X squared times x squared times x squared would be x to the 6th. So there's our inner expression. And so our iterated integral is now going to be the integral from 0 to 1 of 3x to the 4th minus 3/16 x to the 6th dx. If we use the fundamental theorem of calculus on this, then the antiderivative with respect to x will be 3/5 x to the 5 minus 3/16 times 1/7 x to the 7th, evaluated from 0 to 1. If we plug in 1, we're going to get 3/fifths minus 3/16 times 1/7, which would be 3/112ths. If we plug in 0, we're just going to get 0 minus 0, and so we don't need to include those. So we get 3/5 minus 3/112ths. If we put that on a common denominator, 321 560ths. And so that's the integral, double integral over the region R1. Now let's focus on the integral over R2. We have to first describe the region R2 as a vertically simple region. So first, we've got to figure out its lower and upper curves. Well, the upper curve on the second region is the horizontal line y equals 1, and the lower curve is the parabola, which we already figured out was y equals 1/4 x squared. The leftmost side is x equals 1, whereas the rightmost point is the point 2, 1, which means that x is equal to 2. That's the farthest x we get. And so now we've described this as a vertically simple region. Fubini's theorem says that the double integral over it is expressed as an iterated integral. We'll integrate the function 6x squared y with respect to y from the bottom curve to the top curve, and then we will integrate this with respect to x from the left-hand side 1 to the right-hand side 2. All right, well, we're getting old hat at this. Let's focus on the inside integral first. If we anti-differentiate this with respect to y, we'll get 3x squared y squared, evaluated from y equals 1/4 x squared to y equals 1. If we plug in y equals 1, we're just going to get 3x squared. And if we plug in y equals 1/4 x squared, we've already seen that that comes out to being 3/16 x to the 6th. So that's the inside piece. And so the iterated integral will become the integral from 1 to 2 of 3x squared minus 3/16 x to the 6th dx. If we apply the fundamental theorem on this, we're going to get x cubed minus 3/112 x to the 7th, based on the work we did last time, evaluated from 1 to 2. So if we plug in 2, we're going to get 2 cubed, which is 8, minus 3/112 times 2 to the 7th power, which is 128. If we plug in 1, we're going to get 1 minus 3/112. So if we clean this up, we're going to get 403/112. And so that's the second integral value. Hence, the double integral over the region R is simply going to be the sum of these two fractions, 321 560ths, and then 403/112, which if we multiply the top and bottom by 5, is 2015 560ths, giving us a grand total of 2,336 560ths, which can be simplified to being 146 35ths. And so there's our double integral. Now, before we completely relegate this example to the finished pile, it's worth noting that what made this problem so hard was that it wasn't a vertically simple region. However, if we drew horizontal lines, notice that every single horizontal line always has the same left side and the same right side. So this would be horizontally simple. Is there a Fubini's theorem for horizontally simple domains? Turns out that the answer is yes. Let's start off by describing what we mean by a horizontally simple domain in detail. So such a domain will have a horizontal top line, y equals d, and a horizontal bottom line, y equals c. The left side of the region will be described by some curve who passes the horizontal line test. So a curve like that will take the form x equals a of y. It'll be a function of y. And the right side of the region will also pass the horizontal line test. It'll take the form x equals b of y. And so this right here will be our region in question. Such a region is called horizontally simple because every single horizontal line in the region has the same left and right defining curves. If we called this region R, then we could describe this region as a pair of inequalities, just like we did for vertically simple regions. In this case, the y values will go between two fixed numbers, the lowest y value of c and the highest y value of d, whereas the x values will range between their left curve and their right curve. So any region who can be described like this is also a horizontally simple region. If we repeated the procedure we had done earlier in this podcast, or if you go back and look at the podcast once before, it turns out that a double integral over a horizontally simple region can be expressed as an iterated integral. We'll take the function, but now we're going to integrate it with respect to x first, between its left side and its right side. Then we'll take this integral and integrate that with respect to y from the bottom to the top. This formula right here is called Fubini's theorem, and it's valid as long as the function f is continuous. So let's see how this might help us with the previous example. In the previous example, we saw that the region was actually better described as a horizontally simple region. What would this region be? Well, let's set up the pair of inequalities who describe it. Let's first focus on the x values, the two curves. Now the left-hand side right here is the equation y equals x, which is the same thing as saying x equals y. So the left-hand equation is x equals y. Now the right-hand curve, the curve that all the horizontal lines meet on the right-hand side, was given by 4y equals x squared. To make this a horizontally simple region, we have to describe this as in terms of y. So let's solve this for x. So we're going to get x is equal to plus or minus the square root of 4y. That means x is equal to plus or minus 2 times y to the 1/2 power. Now this plus or minus is indicating that there's two parts of the parabola we could be taking a look at, a negative portion and a positive portion. Since all of my x values are positive, let's just toss out that negative value and only focus on 2y to the 1/2. So that becomes the right-hand part of my region. Now that we've got the left and right-hand curves, we can talk about the lowest y value, which is down here at y equals 0, and the largest y value, which apparently is y equals 1. So we've got this described as a horizontally simple region. So then we can apply Fubini's theorem to this. In Fubini's theorem, we'll take the equation 6x squared y and integrate it first with respect to x, from x equals y, the left-hand side, to x equals 2 times y to the 1/2 power, the right-hand side. And then we'll integrate this with respect to y from the bottom 1 or 0 to the top 1. Let's do it. We'll focus on the iterated integral first. If we integrate 6x squared y with respect to x, we're going to get 2x cubed y, which we can then evaluate from x equals y to x equals 2y to the 1/2 power. When we plug in the top value, we're going to have 2 times the quantity 2y to the 1/2 power cubed times y. When we plug in the bottom value, we're going to have 2 times y cubed times y. Now the second expression is easy to simplify. That's 2y to the 4th. On the other hand, this is equal to 2 times, we can put the power on both of these guys since it's multiplication, so we're going to have 2 times 8y to the 3/2 times y, which can be cleaned up as 16y to the 5/2 minus 2y to the 4th. And so that's our inside integral. So now we can complete the iteration by integrating from 0 to 1 the function 16 times y to the 5/2 power minus 2y to the 4th with respect to y. If we apply the fundamental theorem to this, we're going to have 16 times, let's see, that would be y to the 7/5 times 2/7 minus 2/5 times y to the 5th, evaluated from 0 to 1. So if we plug in 1, we're going to have 16 times 2/7 or 32/7 times 1 minus 2/5. When we plug in 0, we're going to get 0 minus 0, so we don't even need to consider it. If we put these things on a common denominator of 35, then we're going to have 160 35ths minus 14 35ths, which gets us 146 35ths. And this is exactly the value we got last time, but at considerably less expense. Find the volume of the solid formed by the portion of the paraboloid z equals 1 minus x squared minus y squared that lies above the x-axis. So, what is this telling us right here? It says that we've got some paraboloid, and if we sketch it, we'll find that it's a paraboloid that has a vertex at 1 unit up, and then sort of opens downwards along the negative z-axis. So an object who's shaped something like this. What we want to do is we want to find the part of this that lives above the x-axis, ignore the bit below, and find the volume of this shape instead. Notice that this, since it's a volume of something above the x-axis but below a surface, this volume could be expressed as a double integral. We would integrate the function 1 minus x squared minus y squared dA over the region R, where R is going to be, well, the region described by the trace at z equals 0. So what is that z equals 0 trace? Well, the z equals 0 trace would be the trace 0 is equal to 1 minus x squared minus y squared, or x squared plus y squared is equal to 1. So that means that this region that we're integrating over is the inside of a circle of radius 1. Let's draw that object and see if we can figure out whether it's horizontally or vertically simple. So this is the region in question. X squared plus y squared equals 1. Now notice that every time I draw a vertical line right here, every vertical line contacts the top half of this circle on the top edge, and the bottom part always contacts the bottom edge of the circle right here. So this is definitely a vertically simple region. Can we find the equations of these curves? Well, let's just solve the circle for the equation y. We get y squared is equal to 1 minus x squared, which means that y is equal to plus or minus the square root of 1 minus x squared. So the positive part is this bit, the negative part is that bit. So this is in fact a vertically simple region. It's the region R equals the y values stay between negative the square root of 1 minus x squared and positive the square root of 1 minus x squared. The x values stay between the leftmost side, which has to be negative 1 because it's a circle of radius 1, and the rightmost side, which is positive 1. So we have a vertically simple region. So now let's integrate this thing. We'll take the function 1 minus x squared minus y squared, and we'll set it up as an iterated integral. According to Fubini's theorem, since this is a vertically simple region, we're going to integrate with respect to the vertical variable first. So we'll integrate it from minus the square root of 1 minus x squared to positive the square root of 1 minus x squared, and then we'll integrate that expression from minus 1 to 1. So let's focus on this bit first. If we integrate this part with respect to y, well, let's see, 1 minus x squared is a constant, so the integral of that will be y. The integral of y squared will be 1/3 y cubed, and so we'll integrate that from, or evaluate that from y equals negative the square root of 1 minus x squared to y equals positive the square root of 1 minus x squared. If we plug in the top limit, we're going to have 1 minus x squared times y, which is 1 minus x squared to the 1/2 power, minus 1/3 y, which is 1 minus x squared to the 1/2 power, cubed. Then we'll subtract what we get when we plug in the bottom. When we plug in the bottom, we're going to have 1 minus x squared times negative 1 minus x squared to the 1/2 power, minus 1/3 of negative 1 minus x squared to the 1/2 power, quantity cubed. So let's clean this thing up here. We have 1 minus x squared times 1 minus x squared to the 1/2 power, that's 1 minus x squared to the 3/2 power, minus 1/3, well, powers raised to powers, we multiply, so this is 1 minus x squared to the 3/2 power. Then we'll have a minus negative, so positive, 1 minus x squared times 1 minus x squared to the 1/2 power is 1 minus x squared to the 3/2 power. And last but not least, we have a negative, negative, negative cubed, which would be negative 1/3 of 1 minus x squared to the 3/2 power. So we have one of these, take away a third of these, added one of these, take away a third of these things. That's 2 minus 2/3, 1 1/3 of these 1 minus x squared to the 3/2. So this is our inside bit. We now need to integrate from minus 1 to 1 the function 4/3 1 minus x squared to the 3/2 power with respect to x. Now we might hope that we could maybe do a u substitution on something like this, u equals 1 minus x squared, but unfortunately, in order to make the substitution work, we're going to need an x dx, and we don't have anyone here. However, this does take the form of a something squared minus something squared to a power over 2. So this is an excellent candidate for trigonometric substitution. The correct substitution to try is theta equals the arc sine of the variable x over the constant 1, or equivalently, x is equal to the sine of theta. If we differentiate both sides with respect to x, then we're going to get that dx is equal to cosine of theta d theta. And so under this substitution, we're going to have 4/3 times 1 minus x, which is the sine of theta squared, to the 3/2 power, times dx, which is the cosine of theta d theta. Now, the whole point of a trigonometric substitution is that the inside part can be simplified using the Pythagorean identity. So we're going to have 4/3 times the cosine of theta squared raised to the 3/2 power times the cosine of theta d theta. Well, cosine squared to the 3/2 power is cosine cubed. Cosine cubed times cosine is simply cosine to the 4th. And so now we need to find an antiderivative of 4/3 cosine to the 4th d theta. Let's pull that 4/3 out to the front and just focus on the integral of cosine of theta to the 4th power d theta. This is a trigonometric integral, but since it only involves one trig function, cosine, to an even power, it's not an easy one to evaluate. The best bet is to either invoke a double angle formula from trig or to apply integration by parts. Since I'd like to focus on integration theory, let me focus on the integration problem, or the integration by parts procedure, and let's just focus on coming up with an antiderivative for the cosine of theta to the 4th power. So I'm going to set up an integration by parts where I'll differentiate and integrate a term. I'll integrate one of the cosines, and I'll differentiate everything else. So the integral of a cosine will get me a sine. The derivative of cosine cubed will get me 3 times cosine of theta squared times the derivative of cosine of theta, which is negative sine. So we'll do one diagonal, one horizontal, plus minus integral. And integration by parts says that the integral of cosine of theta to the 4th is equal to positive cosine of theta cubed times the sine of theta minus the integral of this piece times this piece, which would be negative 3 times the cosine of theta squared times the sine of theta times the sine of theta, d theta. So let me clean this up a little bit. I'll first remove my integration by parts scratch work, and then I'll simply clean up the bottom as sine squared theta, sine of theta squared d theta. Now this doesn't look like much of an improvement, but I could use the Pythagorean identity on the cosine or on the sine squared term and rewrite this as 1 minus the cosine of theta squared d theta. So if I distribute through, we're going to have cosine of theta cubed times the sine of theta plus 3 times the integral of the cosine of theta squared minus 3 times the integral of the cosine of theta times the cosine of theta, or the cosine of theta to the 4th d theta. This bit is one of the terms in the basic 20. This bit is precisely the integral I don't know how to do. If I focus only on the equation inside the box, if I were to add 3 of the integral of cosine to the 4th to both sides, then I would have 4 integrals of cosine to the 4th equal to this expression right here. Now, if I go and I use the formula from the basic 20, the integral of cosine of theta to the squared is 1/2 of theta plus 1/2 sine theta cosine theta. So we could distribute the 3 to all of these pieces, and then divide everything through, divide both sides of the equation by a 4th, and we would have an expression for the integral of cosine of theta to the 4th power. The integral of cosine of theta to the 4th power is 1/4 the cosine of theta cubed times the sine of theta, plus, distributing through, 3/8 of theta plus 3/8 the sine of theta times the cosine of theta. And so, keeping in mind that we actually have this 4/3 who's been patiently waiting out in front the whole time, I'll group that there. And finally, we have an antiderivative. Distributing this thing through the 3 pieces, we will come up with 1/3 cosine of theta cubed times the sine of theta, plus, the 3's will cancel, we'll have 1/2 of theta plus 1/2 the sine of theta times the cosine of theta. Finally, now that we have an antiderivative, we can back substitute and get that this is equal to 1/3 of the cosine of theta, which was the arcsine of x cubed, times the sine of the arcsine of x plus 1/2 times the arcsine of x plus 1/2 times the sine of the arcsine of x times the cosine of the arcsine of x. Of course, given an expression like this, trig of arctrig always simplifies, and so we could simplify this by using the correct triangle, by using a correct trig triangle. If we go back to our original substitution, theta equals the arcsine of x, I can draw a triangle who represents this. Here's the angle theta. It's the angle whose sine, whose opposite over hypotenuse, is x. That means that the missing side of this triangle, according to the Pythagorean theorem, is the square root of 1 minus x squared. And so we can now read off the cosine of this angle, the sine of this angle, the sine of this angle, and the cosine of this angle directly from the triangle. We're going to have 1/3. The cosine of this angle would be the adjacent side, which is 1 minus x squared to the 1/2 power, over 1, quantity cubed, times the sine of the angle. Well, the sine of the arcsine of x is x, plus 1/2 times the arcsine of x, plus 1/2 times the sine of the arcsine of x, which is x, and then the cosine of the arcsine of x we've just worked out as being 1 minus x squared to the 1/2 power. So finally, if we clean this up and rearrange some of the terms, we're going to have 1/2 times the arcsine of x plus 1/2 times x times 1 minus x squared to the 1/2 power plus 1/3 times 1 minus x squared to the 1/2 power to the third, which is the 3/2 power. And so finally, after all that work, we have an antiderivative. And so we can finally evaluate this from -1 to 1. So if we plug in 1, we're going to get 1/2 times the arcsine of 1 plus 1/2 times 1 times 0 to the 1/2 power plus 1/3 times 0 to the 3/2 power. If we plug in -1, we're going to have 1/2 times the arcsine of -1 plus 1/2 times -1 times 0 to the 1/2 power plus 1/3 times 0 to the 3/2 power. So zeros raised to these powers are 0. And so this work, which I will continue up here, becomes 1/2 the arcsine of 1. That's the angle whose sine is 1. That's pi over 2. Minus 1/2 the arcsine of -1. That's the angle whose sine is -1, which is negative pi over 2. And so that gives us a grand total of pi over 4 minus negative pi over 4, or pi over 2. So the volume of the solid is pi over 2 cubic units. Keep in mind the horror of this particular example, because we're going to come back to it in 2 podcasts. Evaluate the iterated integral, the integral from 0 to 1 of the integral from y to 1, e to the minus x squared dx dy. Well, this seems like a pretty straightforward problem. We'll just focus on the inside bit and get cracking at it. So the first thing we need to do is come up with an antiderivative of e to the minus x squared dx. And despite the fact that this looks simple, you might remember from Calc 2 that this is known as the error function. It's a function who doesn't have an elementary antiderivative. We simply cannot work this out with Calc 1 tools. So how blazes are you supposed to work out something like this if we have to invoke a function we don't know? Well, maybe the idea would be to use Fubini's theorem. This is an iterated integral where we've integrated with respect to x first. However, if I saw this particular function and you asked me to do an iterated integral, I'd rather integrate that with respect to y first because it's a constant. So let's just integrate this with respect to y first instead. So we'll do e to the minus x squared. We'll integrate that from 0 to 1 dy, and then we'll integrate this from y to 1 dx. Now I'm not even going to work this out, because I know that this answer is going to be wrong. How do I know that? Well, whatever we're going to get on the inside is kind of irrelevant, but the final answer is going to involve y's in it, because whatever answer we're going to get, we're going to plug in y into it, which means that the final answer isn't a number right here. So what went wrong? What went wrong is that we abused Fubini's theorem. Fubini's theorem says that we can do an iterated integral with respect to y first if this is a double integral over a vertically simple region. And right now, we're somehow not even talking about what's going on at all. So let's take one step back and try to understand what this double integral really means, and then take a step forward on it. It's an iterated integral. So this should be some kind of double integral over some region of the function e to the minus x squared dA. Can we describe what the region is? Well, the first thing I know about it is that it's a horizontally simple region because we were integrating with respect to x. In fact, we would know that this region would have its x values going between the curve x equals y on the left and x equals 1 on the right. The y values would always stay between, well, they're right here in the integral, 0 and 1. So using Fubini's theorem backwards, we're able to figure out what the region in question is. Now let's draw what this region actually is here. We've got the equations, let's see, we have a left-hand equation. The left-hand equation is the equation x equals y. So that's a vertical line. We also have the right-hand equation, the right side of this region, which is the equation x equals 1. So that would be a vertical line right here. We also know that the y values always stay above 0, but below 1. So can you see the region that has all of these properties? We're talking about this triangle right here. This is the region R. Now, if we want to be able to do this double integral over this region with respect to y first, we need to describe it as a vertically simple region. So question 1, is it vertically simple? Yeah. All of the tops of my vertical lines live on the equation x equals y, and all the bottoms of my vertical lines lie on the horizontal line y equals 0. So this region right here, which we originally described as being horizontally simple, can also be described as being vertically simple. To be vertically simple, we'd have to have a top curve. Well, the top curve is going to be y equals x, and a bottom curve y equals 0. The x values will go from x equals 0 on the left-hand side to x equals 1 on the right-hand side. And so we've been able to describe the exact same region two different ways. The upshot, though, is that the second description we've written right here is described as a vertically simple integral, or vertically simple region, sorry. And so Fubini's theorem will allow us to describe the original double integral as an integral of e to the minus x squared, evaluated first with respect to y between 0 and x, and then with respect to x between 0 and 1. So let's do this now. If we focus on the inside integral, the integral of e to the minus x squared dy is just e to the minus x squared y, because e to the minus x squared is a constant, evaluated from 0 to x. So when we plug in x, we're going to get x e to the minus x squared. When we plug in 0, we're going to get 0. And so we've worked out the inner integral. So now the iteration says we just have to integrate from 0 to 1 the function x e to the minus x squared, evaluated or with respect to x. Now this particular problem is an excellent u substitution candidate. If we let u be minus x squared, then the derivative with respect to x would be negative 2x, or negative 1/2 du is equal to x dx. And we do have an x dx in this integral. So under the substitution, x dx is replaced with negative 1/2 du. The integrand becomes e to the u, and so we need to integrate this. The minus 1/2 comes along for the ride. The antiderivative of e to the u is e to the u. If we back substitute, we get minus 1/2 e to the negative x squared, which we can then evaluate from 0 to 1. So when we plug in 1, we're going to get minus 1/2 e to the minus 1. When we plug in 0, we're going to get minus 1/2 e to the 0. Negative negative is positive. That gets me 1/2 minus 1 over 2e. And so there's the value of the iterated integral, but the iterated integral is the same as a double integral over a region, and the double integral over the region is the same as the original iterated integral. And so we've worked this out as being 1/2 times 1 minus 1 over e.